So we'll come back to our part 4, which is our last part for strength property of soil. So we have looked at how to determine the parameters of strength, that is cohesion and internal angle of friction. Then also we looked at how to determine the deformation and elastic loading of sandy soils. So to do that, we said that we need to determine the stress at a point. Is that okay? The vertical stress at a point. So the vertical stress it has two components. It has the stress due to the weight of the soil above that component, and also the stress due to the loading of soil. Okay, the stress increase, which we call the stress increase at that point. Is that okay? So a soil will deform under that stress increase. So how do we determine the effective stress of soil at a point? How do we determine the effective stress of soil at a point? So let us assume that a soil of a given area. Let us assume this is the area of our element, our area A. Is that okay? Our area. So you know that pressure or stress is equal to force divided by area. What is that? Is that okay? And this force is due to the weight of soil. Is that okay? It is due to the weight of soil above the soil. Let us assume this is just the density without the saturation. No more soil without. Let us assume that the groundwater level is at a certain point. Let us have that first condition, that the water level, or we can let us take our particle at this point now. Let's call this a soil before at a certain level W before the saturation. Is that okay? Our soil, our element is here, and it's of area A. Is that okay? So what is force? You know that force is equal to the weight, which is the force due to gravity, which is the weight. Is that okay? And weight is equal to mass times gravity So now for this one, we'll give you the weight of soil. Is that okay? We'll give you the weight of soil. So now what is divided by an area A. But what is mass? So we know that mass is equal to volume density times volume. Is that okay? So when you come and substitute in this function, we shall see that we have our now for this will be that was a force without A. That's let's remove an A here. Let's remove this A here. So without this, our force is equal to M times G. Is that okay? But what is M? M is equal to mass divided by times volume. Is that okay? So now for our pressure, or our stress at any depth, it is equal to force, which is equal to, we substitute this. If we move this and substitute it here for M, so it is equal to density times volume times G. Is that okay? Divided by A. Divided by A. So what is volume? Volume is equal to any depth is equal to depth of the sample. If it is a depth of this is the source depth of the soil sample times area. We give the volume we are considering this. The weight of that volume is exactly that. And if this this sample is of this other height, ZW, is that okay? So when you substitute times area, when you substitute for volume in this place, what do you get? You get our pressure, P, or stress at any point. Pressure P is equal to this one will cancel. This A will cancel with that A when you substitute. Then we shall mean now for rho, density times is equal to unit weight. Now I say that the unit weight is equal to density times gravity. Is that okay? We'll give the unit weight. So therefore, the density will end up with being that is equal to Z W ZW. The W is not working, not writing. And is equal to Z is equal to P is equal to Z W times the unit weight. Unit weight of soil. Now we'll give the pressure. Now for the pressure, the stress at any point, this is Z at any point, is equal to the unit weight of that soil times Z. And we'll give you the pressure, and the pressure of soil above, this pressure at this point above of pressure of soil at this point due to the soil above it. Is that okay? So this is what it is here. The stress at any point Z is equal to unit weight of soil. That's considered this part B. Is that okay? Unit weight of this soil times ZW. Now, for if this is the water level, is that okay? If this is the water level, then remember we are looking at what? At the density. Now, for the density of soil from here up here is the saturated unit to density. Is that okay? Now, for that's why you're getting minus Z plus Z minus W. We'll give you the height from here up to here times its density. Is that okay? That will give the total stress. The total stress of the total pressure at this point due to the weight of this what? Of this soil above it. Is that okay? Then the pore water pressure, now the water is up to this level. Is that okay? They do hydrostatic pressure at this point due to the water will be equal to Z minus W times the unit weight of water. Is that okay? Now what is be the effective? Now for the effective will be equal to the total stress minus the pore water pressure. Is that okay? Which will be equal to this sum here, which is this, minus that. Is that okay? Now, for in the end, when you arrange, what we are going to now for this value is the same value. So therefore, you factorize this out. And that's why we are factorizing. We're factorizing it out. When you multiply, you subtract this minus this to get what we call the submerged unit weight, which will be the what we call the effective unit what? Now, for the effective unit weight is equal to unit weight of water, saturated unit minus unit weight of water, which is this. Now for the effective weight of the effective stress of soil, or the weight of the soil skeleton alone minus water is equal to the unit weight times ZW, this part which is that water, then times the distance from here up to here times the submerged unit weight. Times the submerged, that will give the total stress, the total effective stress at this other point. Is that okay? What we call the overburden stress. And this overburden stress is very important. We shall further say this in our chapter 6 under consolidation, in calculating consolidation, because this is also considered. Okay? What you call this what we call the overburden stress. The overburden stress. So if you can do the example, this example here. So they calculate the effective stress for a soil at a depth of 5 meters in the uniform deposit of soil. Okay, now for the uniform deposit of soil. Now for this soil, now for what if is for now for the specific gravity is the same. Since the specific gravity is not given, therefore assumed to be 2.7. So we have two cases. Now if we want to get the density of soil in this dry, in the bulk unit weight here, and also we need to get also the saturated unit weight here. Is that okay? We know that the bulk unit weight is equal to GS plus SE over 1 plus E. So what we don't have is E. But you know that water content from the equation of water content is equal to SE divided by GS. That is W. Now you can make E the subject. Is that okay? Now for E is equal to W GS over S. Will give you the void what? The void ratio. So with the void ratio determined with S known, now for S we know it, which is 0.6. GS is 2.7, E has been determined as 1.35. Then you can calculate the density, the bulk density of soil above the water table. Then again, you can determine the bulk density below the water table. Is that okay? I mean, for there, we are going to use the saturated unit weight equation, where S is equal to 1. Here, you put S is equal to 1 here, when this is saturated. Is that okay? We have already seen this in our chapter 1, under the phase relationships. Is that okay? So, what we need to know now to calculate the E. The E, when E is equal to 1, when enough for this W, GS. This, remember, this is, we saw this in what? In compaction. Okay? So the time is void ratio. After the void ratio, we substitute in this equation again. Then we can determine what? We can determine the saturated unit weight, the density of soil at this point. So with the density determined, with the density here, then we can determine now the weight, the effective weight, or the overburden stress. The overburden stress at this point of soil, in this point of soil, due to the weight, self-weight of the what? Of soil. To be very simple, it will be this times 2, the effective one, plus 3, that is 5 minus 2, plus 3, times the submerged unit weight, which will be 17.8 minus 9.81 or 9.8. Is that okay? Will give you the effective stress at this point, what we call the effective overburden stress. Let's go through the working. So we determine this. So the first one, the total stress, will be equal to 2, which will be the distance, times the density of this soil, plus 2 times the saturated unit weight, will give the total stress. Then you calculate the pore water pressure, which you give by this. Then to get the effective, will give you the total minus the effective. Alternatively, we can use this formula. Is that okay? So it will give 2 times the times 2 times the density, the bulk unit weight, then into 3 times the submerged, which will be 17.8 minus 9.8. You give you the weight of soil, the stress, the bulk, or the overburden pressure, or the overburden stress at this point due to the weight, the self-weight of the soil above that point. Is that okay? Now these are very important. Yeah? These are very important parameters. So after determining that, that is one. And then the next one is to determine the stress due to the point of the loading. We have determined the stress due to, this one helps us to determine the stress due to the self-weight of the soil. Is that okay? About a point, the effective stress or the overburden pressure due to the self-weight of soil above a point, that point of in the soil you are considering. Is it 2 meters, 5 meters, 6 meters? Is that okay? The weight of soil. Now, the next case is to determine the stress what would be the stress due to the point load application. Is that okay? Now, the distribution of stress within a soil from applied loading or applied surface load or stresses is determined by assuming that the soil is semi-infinite. Okay? It has boundaries. It is homogeneous. It is linear. Isotopy of the properties are the same, and it is elastic material. Remember, you are using elasticity methods. For plastic deformation, we are going to study it under consolidation settlement. Under consolidation and settlement. A semi-infinite mass is bounded on one side. It is semi-infinite. It is bounded on one side. At this side. Now, what it means that the deformation, the lateral deformation won't be determined, but it is finite in one direction, in the vertical, but it's bounded. It is rigid here. Like in a pot, you have a hollow pot.